Okay, so today I will talk about Grothendieck topologies. It will be a very basic talk about the basics of Grothendieck topologies, and I will start from some historical motivation. So there'll be two sides of the story. One of them is fairly short, and it concerns the principal vibrations in algebraic geometry. So so the basic problem is that if we have a vibration in algebraic geometry with some structure group G acting on it, principal vibration, then one would expect that given a small enough Zariski open, this is essential, Zariski open subset of X, one will get a trivialized piece of the bundle. So U over X times W should be trivial. However, Serre discovered that it is not always the case. Meaning that you can have a principal vibration in the sense that you have an action of a group G in fibers, but no Zariski open subset trivializes this vibration. So this was kind of a bummer. And Serre discovered that actually this can be remedied if we consider coverings instead of just open subsets. So if instead of open subset U in X, one considers an unramified covering, then U times W over X becomes trivial. So this is basically where étale topology comes into play. So étale maps are precisely unramified coverings, and you want to trivialize your bundle, and instead of saying that here you should have Zariski open inclusion, you just say, well, okay, we will just have an unramified covering. And this works. So this was one of the ideas that suggested to Grothendieck the initial definition of what we now know as Grothendieck topology. We just replace covers, open covers, with some more general maps. For example, unramified coverings. So that's the first part of historic motivation, principal vibrations in algebraic geometry. Another side of this motivation is more number theoretic. So another is, as usual, we have Galois theory. Somehow it comes to haunt us at every stage of our seminar. We started with Galois theory, and now we come back to Galois theory. So we have an analogy between Galois theory and coverings of topological spaces. Let me briefly recall this analogy. So assume that we have a finite normal extension. The word normal just means that it's a decomposition field for some family of polynomials, but basically any good extension, any algebraic extension you can think of will do. And so we have an inclusion from K to N, and the group, the Galois group, consists of all automorphisms of N over K. So, yeah, and we have a Galois correspondence, which says that we have correspondence between subgroups of the Galois group and subfields of the form like this. So this is a number theoretic story. Galois correspondence, probably you all know it. And we have also a topological story. So this was number theoretic. And now topological story is fairly similar, but it obviously should be opposite, because fields are fields of functions and spaces are spaces. So it's a bit of an opposite story. We have the following map, which is called covering, if for small enough neighborhood, the pullback becomes just a disjoint union of copies of U. So this is what the covering is, and the covering group G, which is somehow analogous to the Galois group. Covering group consists of deck transformations. Assume additionally that rho is regular. That's somehow like a normality assumption on the extension of fields. So the condition of regularity says that a fundamental group of the total space of a covering should be normal inside of the fundamental group of the base. And so subgroups in here correspond to, sorry. So subgroups here correspond to intermediate coverings. Where y prime is defined precisely as a quotient of y by h action. I'm not sure that it's useful, but I will just recall some basic facts. I mean, probably you all know this, but still I will just briefly recall it. Okay. So clearly we just had some dualization happen. So we have duality between fields and spaces. And basically what we have is that in spaces we have a splitting. So and in fields, we don't have a splitting, but if we embed fields into a larger category of commutative algebras, then after suitable extension, we also have a splitting. So it all goes in the opposite direction. So we just include rings into the coproduct of rings, which is a tensor product. And we get a splitting, meaning that have a projection like this. So for spaces, we have the following statement. Over a small enough neighborhood of a point in the base, we have a splitting of the total space restricted to this neighborhood into disjoint union of such neighborhoods. This is all well and trivial, but for fields, we also have something similar. We just need to consider an extension which is large enough to be the splitting field. So the tensor product of this extension with n splits into copies of this large field. So this is basically, this is not completely dual to what we had for topological spaces. So here we had a co-product, and here we have a product, and it splits into the product of different copies of the same field. So for example, if L was generated as an extension of the form K of X over F, where F is some annihilation polynomial for the element theta, then N will be just the field, then N will be just the decomposition field of F. And if we consider this tensor product, then what we will get is just the quotient of the polynomial ring over all adjoints of the element theta. And this is precisely a product of some of m copies of n. So why am I telling this? This is some basic stuff from course on algebra and topology. Basically, the reason is that the duality, which I was saying takes place before, it actually fails. Why it fails? Well, to simply put it, here we had an inclusion of an open neighborhood into a larger space. And if we dualize it, we should have something like a surjection, an epimorphism in fields, and something like this. But clearly, this is not the case, because instead of an epimorphism, we also have an injection. Actually, there is no such thing as an epimorphism of fields. We can only have an isomorphism of fields. Actually, this doesn't work. And instead, we have a diagram like this. And this is another instance where Grothendieck topology becomes useful. Because here, instead of considering epimorphisms, it is useful to consider more general maps like monomorphisms. And so, another way to fix it is to replace here open inclusions with more general maps. So basically, this was motivation. The last part was somewhat garbled, but this is the motivation of why we need more general maps than just open inclusions when we're talking about, for example, topological spaces or topological spaces with some exotic topology like Zariski topology. Okay. But actually, this idea works in arbitrary category with pullbacks. So the idea to have general endless maps called covers works in any category with pullbacks. So what we do, we say that, okay, we want to have some family S. Indexed by the set I. So C is just an object in the category C calligraphic. And S is just some distinguished family. We say that, okay, this family is a cover. We don't explain our motivation, we just say, okay, this is a cover. And then K of C is a collection of all such families. So now, given this datum, we want to explain what is, for example, sheaf on C. So the category of pre-sheaves on C, calligraphic is just category of functors from the opposite category to sets. And now we want to explain what is a sheaf. So let me recall what was a sheaf. So we had an open covering, UI, and a family of elements, xj in PU of j, uj, j9, such that their restrictions were compatible on intersections. Then, as Misha explained, there exists X, which is a collation of all these elements. Well, let's do the very same thing. We just say that instead of open covers, we have some covers. So we have an intersection. An intersection in highbrow language is just a Hilbert product. And we apply the functor P, the very same pre-sheaf. Everything changes direction because it's a pre-sheaf. Now we just do the same thing. We say that if we had a family of elements such that the restriction maps, the restriction maps are precisely those guys. If the restriction map gave the same thing on intersections, then there exists unique collation in this set, which is a value on the whole object which we tried to cover with our family. So the difference is minimal. Yeah, and of course, so this is fj, fi, and this object is precisely such that fi of x is precisely xi. So the restriction coincides with these elements which we had. So this is equivalent in categorical terms to the fact that PC is an equalizer of the following diagram. Yeah, so that's basically it. We discovered how to define sheaves if we're just given some covering family for an object. That's basically the whole point of Grothendieck topology, that you just define sheaves abstractly and assuming that you're given some families of covering objects or some families of covering morphisms. Okay, so let's do some proper theory of Grothendieck topologies now. So this was somewhat of a motivation. Now we're just going to rigorously define everything that was said above. So Grothendieck topologies. So we have a unit embedding into the functor category. And we recall that a sieve on C, which is an object of the category C, calligraphed, curly, is precisely a subfunctor. It's just a subfunctor of the functor of the representable functor which corresponds to this object. More concrete description of a sieve says that so concretely, sieve can be given by a family of morphisms with codomain C, such that Fns implies that Fg is an S, or equivalently that S forms a right ideal inside of morphisms of C. So one operation we can do with sieves is a pullback. So given as sieve C and H from D to C, we can define a pullback sieve H upper star S as the following. So the codomain of G should be D, and if we compose it with H, we should get something in S. And so this is a sieve. It is directly verifiable that this is a sieve on D. Okay, so now we're ready to define what is a Grothendieck topology. Category C. Is the function. G which assigns to each object C inside of C curly a collection J of C thieves such that the following three axioms are satisfied. Okay, so let's introduce the axioms of Grothendieck topology. First, TC, which is just a collection of all F with codomain C, belongs to GC. So if we take all morphisms which go to C, we get a C on C for any Grothendieck topology. Second is that if S belongs to this distinguished collection of sieves, then the pullback sieve belongs to this distinguished collection of sieves, but for the object we pull the sieve back to. Finally, the third axiom states that we can check that certain sieve belongs to this distinguished collection. So R is just some sieve on C. Then R belongs to G of C. If and only if H star R belongs to G of D for any map from the sieve S. So one direction is obvious if R belongs, so it's not really an axiom, it's partly a proposition. If R belongs to this distinguished collection, then of course its pullback also belongs to the distinguished collection with respect to any morphism, not necessarily from S. However, the axiom says that the converse holds. So if we pull back this sieve to along any morphism in S, we should once again get a sieve in, and we get a sieve in the collection, then the initial sieve was also in the collection. So I think that yeah, so later I will give an example with topological spaces, which will somehow clarify things. It will explain on the put examples from usual topology from this play with open sets that actually these axioms are nothing but usual conditions we have for open covers of a topological space. However, for now, I will prove one minor lemma. So if we have a sieve and we have a larger sieve, then it automatically belongs to this collection of sieves. Okay, let's prove this. Let H be a morphism from D to C. H belongs to S. Then the unit morphism belongs to the pullback. And hence, H of S is the maximal C. Because if unit belongs to an ideal, the ideal corresponds to the whole ring. The logic is the very same here. If we have the unit morphism, then we have all other morphisms as well. Since HS is smaller than HR, we have HR belongs to, HR is also a maximal sieve, so it coincides with the maximal sieve on D. And thus, by axiom 3 implies that R belongs to G of C. So this is quite an elementary proof. And we established the following lemma. This lemma and axiom 3 implies, oh, well, I don't think that we will need it, so I will just skip it. We can modify the axiom 3, but I don't think that it will be necessary, at least right now. So let me give a definition of a site. Site is a pair consisting of a small category and Grothendieck topology on it. Let's see, small J Grothendieck topology. And we will say that if S belongs to J of C, then S covers C. Or in other words, S is covering C for C. Okay. So I think that now I can state the following fact. So any two covers or any two sieves have a common refinement. So that will be not an axiom, but actually a proposition, but I will denote it by saying in the same way as axioms, because it is somewhat fundamental to Grothendieck topologies. So any two covers R and S G of C have a common refinement, or more precisely, their intersection also belongs to G of C. Let's prove this. So we have a morphism in R. And we get that a pullback of this intersection coincides with the pullback of S, and it belongs to J of D by axiom 2 of Grothendieck topology. Now, by axiom 3, the intersection, since its pullback always belongs to the distinguished family of sieves, is also a sieve now on the object C. So this is the elementary proof of this fourth property, fourth axiom of Grothendieck topology. Okay, so now we finally arrived to an example with topological spaces. Consider a category O of X of open subsets in topological space X. Then S covers Q. So this is the category C. If and only if Q is just the union of elements of S.
So sorry, why we have a quality above F star of R? Yes. Mm-hmm.
Okay, let's verify it. That's a great question. I didn't bother myself with verifying it, so now it will be a kind of experiment. But let's try to do this. So let's recall what a pullback is. It consists of all elements of all H in morphisms of C, such that codomain of H equals D, and the composition FH belongs to this intersection, right? So similarly, we have H C1 on domain of H equals T. FH belongs to S. Okay, now let's note that F itself belongs to R. Okay. So now we just observed that, wait a moment. So by definition of a sieve, we have that a sieve is a right ideal, right? So actually FH not only belongs to S, but it also belongs to R. Is it clear? That was just one moment. It was here. So F in S means that FG is also in S. S forms a right ideal in C. Okay, so that means that actually FH belongs both to S and R, right? So it belongs to S intercepted with R. And I think that proves the equality.
Thank you.
Mm-hmm. Thank you for the question. I didn't check it. Now I'm sure that this is true. So thank you. Okay, so let's go back to our topological example. Okay, so the category now is the category of open subsets in a topological space. And we say that a sieve, that we have a covering sieve, and if and only if the elements of this sieve cover this object in the usual sense. Now we note that, so this will be somewhat of a segue to the notion of a basis for Grothendieck topology. So let's note that any collection U fractured of open subsets in OVETs generates a sieve by a formula so yeah. So it generates a sieve by a formula F belongs to S of U. So we have, obviously, we have an inclusion UI to U. So it generates a sieve on, so if U is a covering of some open subset U, it generates a sieve by a formula F belongs to S of U if and only if F can be presented as a composition Fi with F F line for some Fi from UI to U. So this becomes more digestible if we consider the following pictures. So we have UIs, U1, U2, U3. And basically what we say is that the sieve generated by these open subsets consists precisely of such open subsets which fit into the holes. So we can view UIs as holes, and then we say that we can identify the subset and the inclusion morphism. F belongs to the sieve if and only if it fits into one of UIs. Okay. So that's basically the rationale behind the name sieve. You just take open subsets and then you push morphisms through them. So if you can push a morphism, then this morphism belongs to a sieve. That's the reasoning. Okay. So as is with usual topology, we want to get some manageable description of topology. Sorry for this tautological sentence, but the idea is that Grothendieck topology is huge, and it is useful to be able to define Grothendieck topology by some small collections of morphisms and not specifying all sieves which belong to topology on an object. So this inspires the notion of the basis for Grothendieck topology. C should be a category with pullbacks, as usual. And basis of a Grothendieck topology on C with pullbacks is a function K which assigns to an object C in C curly collection KC of morphisms of families of morphisms. So it's similar to just regular topology, but collections are smaller. Sorry, not the collections are smaller, but K of C is smaller than J of C. Of families of morphisms. With codomain C, such that So we have a collection of axioms, 3 axioms once again. So each isomorphism forms an element of K of C. So all isomorphisms should be included into K of C. The second condition is similar to the stability axiom. So if Fi is similar to second axiom of Grothendieck topology, this is sometimes called stability axiom. So if we have a collection which belongs to the basis of topology of C, and we have any morphism G from D to C, then the family consisting of projections of pullbacks also belongs to the basis of topology, now on the object G. And finally, the third axiom says that if we have a family Fi from Ci to C, which belongs to the basis of topology on C, and for any I in I capital, we have Tij to Ci. There is something one false here. Yes, because such that it also belongs to the basis of topology, then the family the composite family from Dij to C for I in I and J in I capital I small belongs to QC. So this is an analog of axiom 3 for Grothendieck topologies. And it looks scary and depressing. But we can actually deduce, I think we can actually deduce the similarity here that think for a bit. Yeah, so basically the idea is that we can refine elements of the basis. This is basically a covering of each separate CI. And we had a covering of C with cover of C with CIs. So if we have a cover of each of CIs and we had a cover of C, then we can mesh them together and get a finer cover of the whole object C. So let me draw a picture. I don't know, maybe everybody already figured out what I mean. So C1, C2, C3, C4. Then each of them is covered by C1J. And we get a cover of the whole C by these smaller subsets. Okay. So now we can give an alternative definition and say that a site is a small category together with the basis of Grothendieck topology. K of C is covering families, or just covers. Note that the relationship between Grothendieck topology and basis of Grothendieck topology is not straightforward. In particular, it differs from the relationship between basis of topology in general topology and topology in general topology. So in general topology, the topology itself forms its own basis. Here, it is not the case because we have this pesky axiom number 1 prime. So from 1 prime follows that Grothendieck topology does not form basis Grothendieck topology. That's just because we never, because, well, an isomorphism, which should belong to the basis of Grothendieck topology, a basis of Grothendieck topology, never actually forms a sieve. So we have just one morphism and it can't form a sieve, of course. Yeah. That's the crucial difference. However, in the opposite direction, it works. So a basis of Grothendieck topology indeed defines the Grothendieck topology. Let me give this procedure now. So So we define Grothendieck topology in the following manner. S belongs to J of C if and only if there is R in K of C such that R is smaller than S. So in putting it in words, a thief is covering if it contains the cover.
Could you recall what is the K of C?
K of C is basis of Grothendieck topology. So once again, what we're doing now, we have a basis of Grothendieck topology. This guy here. We want to construct a Grothendieck topology J of C. This is the construction. We say that a C belongs to J of C. So what we do? K is a basis. We want J. What we do to get J? Well, we say that S belongs to J of C if and only if there is such R, which is just a cover, an element of K of C, such that R is contained in S.
Okay.
Okay. Great. Okay, so let's verify that we indeed got a Grothendieck topology. We do it only for axiom number 2. So if S belongs to J of C and G is an arbitrary morphism from T to C, we choose R in S such that R belongs to K of C. We can do this because S belongs to J of C. So by definition, there is such R, which is contained in S, and it belongs to K of C. And then let T, which belongs to K of D, be a full back cover T. Then T contained in G star of S, and thus G star of S belongs to J of C. So we verified the stability axiom. All other axioms are verified analogously. Okay. Now, let me note that if we have a Grothendieck topology, then well, I'm not sure that we will actually need this. Maybe I will just give some examples. So I'll just briefly remark that if J is a Grothendieck topology, then we have a maximal basis for this topology. So this basis is defined like this. R belongs to K of C. R belongs to J of C. And R round brackets is just the following. Consists of all Fg for F and R, and domain of F coincides with the domain of G. So that's basically an ideal generated by R, and we just say that R is a cover if and only if the sieve which is generated by this cover belongs to Grothendieck topology. Okay. So let me just briefly state that so remember that we had the following statement that if R and S belongs to J of C, then the intersection of R and S also belongs to J of C. So for bases, this doesn't work. Obviously, if you have two covers, you can't just intersect them set theoretically and expect it to give a cover, because very rarely two covers have large enough intersection to satisfy this condition. However, we can introduce the notion of refinement. So we say that Fi from Ci to C refines G from G to C if for any Fi factors, if any Fi factors through some Gj. So this coincides with our usual expectations of refinement. If we view Gj's as inclusion morphisms, for example, then this condition just says that we have the inclusion of each element of this cover into some element of the larger open cover. So the notion of refinement coincides with usual expectations for refinement in usual topology. Okay, so then we have the following statement for basis of topologies. For any R and P in K of C, there is a common refinement in KFC. So the proof is straightforward, and it uses the notion of maximal basis. So you just take R, two ideals R and P. You recall that they both belong to J of C. And then you just say that, well, these two guys, if we intersect them, we get something in J of C. Well, that's great. Now we just need to remember that by definition of J of C, there is some T which belongs to K of C, such that it is contained in the intersection. Well, this T is the refinement. Well, not the refinement, but a refinement. Okay. So we've proved just very natural statement that if you have two covers, you abstractly can prove that we have a common refinement to covers. Okay, so let's finish my today's talk with some more examples. Okay, so examples. So if T is a small category, then we have a minimal Grothendieck topology, which just consists of minimal topology consists of maximal C for each object. Minimal topology. If so, also we can perform the following construction. So big site topological spaces. So let T be a category, be a small category of topological spaces. Closed undertaking finite limits and open subspaces. So, for example, T can be chosen to be a category of countable Hausdorff spaces. Then we can define a basis of topology for T. with the following formula. So it covers X if it covers X in the usual sense. So first of all, this should be an open inclusion. And second, the union of all fi's of ui of yi should give X. So that's the definition of the Grothendieck topology on a large site of topological spaces. Why we need this? Well, basically because if we want to define a sheaf of continuous functions on all spaces together, then we need some kind of site structure on the whole category of topological spaces and not merely on given category of open subsets of a topological space. Now, an important remark. To define Grothendieck topology, we in fact need only pullbacks from the form so on the pullbacks of the form like this. And this is great because it means that we don't need all pullbacks. And we can take a category which is not closed under pullbacks, for example, category of manifolds where the intersection of non-transversal manifolds does not exist. However, there is always such a pullback. And it means that we can define a site structure on the category of manifolds. So this is great. And then we can work with, for example, sheaves of infinitely differentiable functions and stuff like that using site structure. Okay. Now I think I will give another example. So example C. Finer topology on the category. Finer topology. The category. Of well, this category of topological spaces is a topology which is given by the following basis. On the category T, the topology given by A prime, which consists of fi's from ui to x so it belongs to k prime of x if and only if f from the disjoint union of ui's to x is an open surjection. So it's a basis because if we consider a pullback of an open surjection along any morphism, along any continuous map, then we will once again get an open surjection. So this proves that K prime is actually a basis of topology. Okay. I think that I can stop here. Next time, I don't know. Maybe Kirill will tell us something about quasi-categories, or I will continue the story about Grothendieck topologies. In particular, I have in mind a concrete example. So next time, an example of the risky topology on schemes. Okay, so this will be a very detailed exposition of what a concrete Grothendieck topology looks like. Okay, are there any questions, suggestions, remarks? Okay.